Kevin. Welcome to my cave. In the last couple of episodes, we looked at several transistor circuits and were able to come up with pretty good predictions for their performance with stiff low impedance inputs and light high impedance loads. Today I want to get into analyzing how they perform with high impedance sources or low impedance loads to reveal what some of the limitations are and take our modeling up one level. To do this, we'll have to introduce a property of a transistor called beta, also called H sub Fe. If we look at any transistor circuit and let I sub B be the base current and I sub C be the collector current, then beta is the ratio of the collector current I sub C to the base current I sub B. If we look at our picture of transistor person, we'll see this equation written on the wall. For the moment, we'll think of beta as a constant. We can think of this as giving transistor person a new job description. Adjust the resistance between collector and emitter so that the ratio of currents is beta. We still need to assume that the base emitter diode behaves like a diode. That is to say, it adjusts its resistance to keep its forward voltage drop constant. It's a boring job, but transistor person is infinitely patient. Let's take a look at what this means in practice. We'll start by building a saturated switch pretty much like the one from the last episode. We'll wire a resistor to the 5-volt supply to serve as a load and connect in a meter to monitor the output current. And I'll use a potentiometer and a series resistor to create a varying input current. I'm intentionally using big resistor values here to show the effect of a small base current. I'll monitor that base current with a second meter. I'll set this up on the breadboard and do the usual procedure of twisting the pot and recording the currents in a spreadsheet. Back in a moment. I'm not going to bore you with the whole procedure of twisting and reading meters and writing down and typing, but the result was a graph in a spreadsheet. Here it is on the screen now. The x-axis is the base current going in, and the y-axis is the collector current coming out. With the understanding of the transistor we had in the last episode, we'd expect the collector current to be constant, a little under 5 milliamps, but we see that behavior only once the base current reaches a certain minimum level. Before that point, we see that the graph is a nearly straight line, and we define beta to be the slope of that line. So in this circuit, the transistor's beta appears to be about 260. And beta defines the amount of current that the collector will pass when the transistor is in the active region. We can see why our previous understanding worked for the saturated switch. The amount of current needed to drive the transistor into saturation is tiny. Here, it's about 20 microamperes. And that's how we got away with ignoring beta so far. It's because it's typically a big number, so base currents are typically tiny. For a typical general-purpose transistor, handling small signals, beta will be at least 100, and that's what we were looking at last time. But for a big power transistor, switching several amperes of current, beta might be as low as 20. We definitely do need to worry about beta then. If we're switching a 10 amp output, we'll need half an amp at the base to do it. Put a pin in that. I'll show later how to work around that problem, by using a second transistor. The formula involving beta is usually the first thing you see when an electronics course gets to transistors. But here we are 5 episodes in, and I've left it until now. There's a simple reason. We never really know what the value of beta is. It depends on temperature. It depends on collector current. It varies from device to device, even in the same production lot. And sometimes I think it depends on the phase of the moon. So what we need to do is design our circuits so that they continue to work as long as beta is big enough, and then choose a conservative value for big enough. Now let's move on to looking at the emitter follower. Last time, all that we could say is that the output voltage with no load is a diode drop below the input voltage. And we waved our hands and said that the transistor base draws very little current, while the emitter can source a lot of current. We'll bring in the current regulation the transistor person is doing. Applying Kirchhoff's current law to the transistor gives us the emitter current. Now we can compute what load the follower will present to its source, and what effect a load will have on the follower. We'll start with the input impedance. Hook up a load R sub L to the follower. Ohm's law gives us the voltage at the emitter, and we add the diode drop to get the voltage at the base. The voltage breaks down to the constant diode drop that we always have to account for, plus a term that looks just like Ohm's law with the load multiplied by beta plus 1. That gives us the input impedance that we wanted. To figure the output impedance, we start by adding a source with a known impedance R sub S. We begin with the same basic facts, written a little differently. Transistor person and Kirchhoff still keep the emitter current equal to the base current times beta plus 1. Ohm's law determines the voltage drop across the source impedance, and the base emitter diode still gives a constant voltage drop. Substitute the base current into the Ohm's law formula, and substitute the result into the equation with the diode drop. We get a term with the open circuit voltage, and a term that's just like Ohm's law giving the output impedance. Just as the input impedance was the load impedance times beta plus 1, the output impedance is the source impedance divided by beta plus 1. Instead of thinking of the follower as a current amplifier, it's equally valid to think of it as an impedance transformer. It multiplies the load impedance by beta plus 1 and divides the source impedance by the same factor. It's as if the transistor is a telescope. When we look into the input, we see the load impedance hugely magnified. When we look into the output, we're looking into the wrong end of the telescope. We see a greatly shrunken copy of the source impedance. But we shouldn't believe our calculations. Let's go to the cave and verify this experimentally. I'll try to estimate transistor beta by measuring input and output impedances, and compare that with the number I got by measuring currents. I'll be happy if they agree within 10% or so, because there are so many extraneous factors influencing the measurement. I've breadboarded the follower with the exact same transistor that I used for the switch. The collector of the transistor is tied to the plus 12 volt supply, and the emitter is pulled down to the minus 12 volt supply through a 3.3 kilo ohm resistor. My function generator is connected to the base of the transistor through a resistor. I'll start with 330 kilo ohms. I've built a load circuit consisting of a 1K resistor to ground, in series with a 10 microfarad non-polarized capacitor. The capacitor is big enough that we can ignore it at audio frequencies, while it still blocks DC so the load won't disturb the biasing. The load is connected to the transistor emitter with a jumper. I'll start with the jumper removed. If I probe the signal generator output and the transistor base with 2 channels of my oscilloscope, I'm essentially measuring a voltage divider with the unknown input impedance of the follower. First, I'll put the 2 channels on an XY display. The Lissajous figure is almost a straight line, so we can treat the input impedance as a pure resistance. With all the stray capacitance in a breadboard circuit, I always like to check. Now I'll switch to displaying the input and output as a time series. The scope tells me that the input amplitude is 5.97 volts, which is just under the 6 volts I set on the function generator. The amplitude of the wave at the base is 4.26 volts. We can set up the equation for a voltage divider and solve it for the unknown impedance Z sub in, plugging in the known values. The input impedance is the 3.3 kilo ohm load impedance times beta plus 1. That gives me a beta of 248, where I calculated 260 before. That's only about 5% off. I'll take it. Now let's look at the output impedance. I'm going to have to work a little harder here. An emitter follower doesn't actually follow unless the transistor is passing some current, so I need a load on the output always. I'll estimate the output impedance by comparing the output voltage between 2 different loads. I'll pull out the 330 kilo ohm source resistance and replace it with a 33 kilo ohm one. I'll take 2 sets of measurements, one with just the 3.3 kilo ohm emitter resistor, and one with the jumper in place, so that there's an additional 1 kilo ohm load at signal frequencies. Since the capacitor is very close to a short circuit at signal frequencies, The resulting load will be very close to a pure resistance of 767 ohms. So what we'll be doing is analyzing two voltage dividers. The first will have a 3.3 kilo ohm resistor on its lower leg, and the second will have a 767 ohm resistor. They're both driven with a circuit that has an unknown open circuit voltage, V sub OC, and that unknown open circuit voltage pushes a current through an unknown equivalent resistance R sub S. We can use the usual equation for a voltage divider. We can solve the two simultaneous equations for the Thevenin equivalent voltage and resistance of the follower. We know the values of R1 and R2. Let's measure V1 and V2, and we can find V sub OC and R sub S. Probing the signal generator and the transistor's output without the added load connected, I see an output amplitude of 5.6 volts peak to peak. Probing the circuit with the load jumper connected, I see the output drop to precisely 5 volts. Plugging in these values gives an open circuit voltage of 5.81 volts and an equivalent resistance of 124 ohms. With our base resistor of 33 kilo ohms, that works out to a beta of 264. Measuring currents, I'd got a value of 260, so I'm happy with this value. To summarize, we've looked at three ways to measure a transistor's beta: measuring its base and collector current directly, measuring the input impedance of a follower driving a known load, and measuring the output impedance of a follower driven by a known source. The three gave values that agree pretty well when I tried them in the cave. Our main takeaways from this whole episode are that, all else being equal, when a transistor is in the active region, collector current is proportional to base current. Even though we don't know beta, the constant of proportionality, we can generally design circuits so that they work as long as it's big enough. This is mostly an issue for the saturated switch, where beta limits how much current the switch can put out. An emitter follower can be thought of as transforming impedances. The input impedance is beta plus 1 times the load impedance, or the output impedance is the source impedance divided by beta plus 1. This has turned into a much longer episode than I expected, and I think I need to cut it off here and cover more about beta in the next episode. I plan to quickly visit what beta means to the common emitter amplifier, examine some ideas for what to do when beta isn't big enough, and take a sneak peek at where the proportionality breaks down. Until then, stay tuned, stay safe, stay healthy, stay curious, and take care of one another. Bye.